This was in the semester test last year, and before that I gave it to the extended students to do. You'll see it's quite a difficult problem, but everyone was of the opinion that after they did this problem, they understood rotational motion. So I think it's a good example of a fairly difficult problem, but if you can master this problem, you're pretty much okay with rotational motion. So the problem is as follows. Here we've got a bridge, which sorry, is there a question? Here we've got a bridge. So the bridge is over some sort of moat with water. It's pivoted so it can rotate around that point. Here we've got a cable tied to the other end of this bridge. It's strung over a pulley, like so. And here we attach a counterweight of a certain mass. Right, so the idea here is that the counterweight is heavy enough to lift the bridge up. Now we have some information. We have that the counterweight has got a mass of 3,000 kilograms, so 3 tons. We've got that, the cable itself, we don't worry about, its mass is negligible. This pulley has got a mass NP, and it's got a radius of 2 meters. The bridge we can model as a uniform rigid rod that has got a length of 4 meters. 4, not 5, 4 meters. The mass of the bridge is equals to 2,000 kilograms, so 2 tons. And at this instant that we see here, we've got that. So at this instant, the bridge is starting to rotate, and at this instant, it's got an angular acceleration equals to 1 radian per second squared. Right, so this is all the information that's given. We don't know the mass of the pulley, and what we are asked to calculate is the magnitude of the tension in the cable between the bridge and the pulley at this instant. So there's a tension in the cable pulling the bridge upwards. Let's call that T1. And similarly, there's a tension in the cable downwards. So let's call that T1 as well. Okay, remember this is a single piece of cable, it's not allowed to switch a break. So in that little segment, the tensions must be the same everywhere. And we must now calculate that tension. So what will make sense, if I know the angular acceleration and I know the moment of inertia, I know the torque on this bridge. There will be 2 forces producing the torque. One will be just the weight of the bridge itself, because if that cable wasn't there, the bridge would fall down into the water. So the weight of the bridge itself provides a torque, and the cable, the tension in the cable provides a torque as well. And the 2 balance out in such a way that the bridge rotates upwards. So it seems to me to be a good place to start to calculate the total torque on the bridge. Now one question, if I want to look at the weight of the bridge, yes? The question is to calculate the tension in the cable T1. So just write it down. So we need to calculate T1. So if I want to view the weight as producing the torque, where would the point of application of the weight be on the bridge? Sorry? So if you, for example, take your pen and you balance it on your finger, you know it's perfectly balanced if your finger is just over the center of mass. So if if my pen is perched on my finger like this, there's no torque on it. So the force from my finger on the pen must be equally matched by the weight of the pen, and they have the same point of application. So because I can balance an object by supporting it at the center of mass, we can view the weight of that object as being applied to its center of mass. So if I want to draw, if I draw just the bridge on its own, so there's just the bridge, we will have the weight applied at its center of mass, which is if this bridge has got a uniform mass distribution, that will be at the geometric center of the bridge. So you will have the mass of the bridge times G downwards. And we've got the tension in the rope or cable T1 upwards. And yes, there's also a normal force from this pivot point, but because the force is applied at the pivot point, it cannot produce a torque because there's no separation between the point of application and the pivot point. So if this is the geometrical center of the bridge, then that distance will be half the length of the bridge. And we know that the full length of the bridge is 4 meters. Now let's use the convention that a counterclockwise torque, like so, will be positive, or a torque that produces a counterclockwise rotation you're going to take as positive, and a torque that produces a clockwise rotation we're going to take as negative. So we can see the weight of the bridge will try to cause a clockwise rotation. So this is going to produce a negative torque. The tension is going to produce a counterclockwise rotation, so that will produce a positive torque. So we also know that, okay, so there's our pivot point. So the total torque on the bridge is equal to the torque produced by the tension. That's just T1 times the length of the bridge, because that's how far this away from the pivot point this force is applied. The weight we said is going to be a negative torque. It's applied at half the distance away from the pivot point, and it's equal to the mass of the bridge times G, that's the weight. So this is the total torque of the bridge, on the bridge. And we know this must be equals to the moment of inertia of the bridge times its angular acceleration. Now, if we take this bridge as a uniform rod, you can go look it up in a table. Its moment of inertia will be equals to 1/3 of its mass times the square of its length. So that you can go look up in a table, or it will be given to you as that just purely depends on the geometry of the bridge. In this case, it's a uniform rod, so you can go look up its moment of inertia. So we can write this even more simply. So this will be equals to the moment of inertia, which is equals to 1/3 times the mass of the bridge times the square of its length, and we are given the angular acceleration as being, well, we can substitute all the numbers in now. So let's see what is known. So we don't know the tension, we know the length, we know that, we know the mass of the bridge, we know G. We know the moment of inertia because we know this, we know that, and we know that. So we've got enough information to calculate the tension. So we've got that T1 times 4 meters, that's the length of the bridge, minus 4 divided by 2, so that's half a length, it's 2 meters. Mass of the bridge is 2,000 kilograms, gravitational acceleration is 9.8 meters per second squared. This is equals to the moment of inertia, which is 1/3 times the mass of the bridge, which is 2,000 kgs, length of the bridge squared, so this is 4 squared, and our angular acceleration is 1 radian per second squared. So, a lot of numbers, but the only unknown now is tension, and you can solve this. What you find is that the tension in the cable is going to be equals to 12,466.7 newtons. So it's a mouthful. It's not simple, but it is, if you look at it, it's simply Newton's second law, but now with the added complication of rotation. So Instead of forces, we've got torques. Instead of masses, we've got moments of inertia. Instead of straight line acceleration, we've got angular acceleration. Now, this is not the end of it. The next question, is we must now calculate the acceleration of this mass. So I must calculate, so this mass will be moving downwards with a certain acceleration, and I must calculate the acceleration of the mass. Okay, any ideas how to do this? So, yes. That's fine. So remember, how can we relate something like a straight line acceleration to an angular acceleration? So think about this. If this cable is not allowed to stretch or break or slip, if this end of the bridge moves upwards by a slight infinitesimal amount, this mass must move downwards by the same amount. So the rate at which the bridge moves upward instantaneously over there must be equal to the rate at which this mass moves downwards instantaneously over there. So the tangential acceleration of this point on the bridge is equal to the downwards acceleration of the mass, because that's the only way that the cable is allowed to remain unstretched and it doesn't slip on the pulley. So the tangential acceleration of this end of the bridge is just equals to its length times the angular acceleration of the bridge. So this is equals to 4 times 1. So the tangential acceleration is 4 meters per second squared, and this must be equals to the acceleration of the mass, because if it's not so, it means this point is instantaneously moving upwards by more or less than this mass is instantaneously moving downwards. That's not allowed to happen if the cable is to remain unstretched. So actually, with just a little bit of thinking, quite easy to calculate the tangential acceleration of the mass. The last thing that we need to calculate is the tension in this side, in this cable. So let's call that T2. So there's tension upwards, and there's a tension downwards. So how to calculate that? Well, it's actually quite easy. We don't have to revert to anything new. We know the total acceleration of this mass. So from Newton's second law, purely, if I need to calculate T2, from Newton's second law, I know that the weight of this mass minus whatever that tension is must be equals to mass times acceleration. I know this is 3,000 kilograms. G is as ever 9.8 minus this tension is equals to 3,000 times the acceleration that we just calculated, which is 4, and we can then solve for that tension, and you find it's equals to 17,400 Newton. So this is an interesting complication. We find that the same cable has got a tension on this side of the pulley and a tension on that side of the pulley, which is not necessarily equal. Does this make sense? Yes? No? Okay, let's first think about this in terms of just the pulley rotating. The pulley has got a mass, so it has got an inertial property. In order to rotate it, I must have the resultant torque. To have resultant torque, I cannot have that the two tensions are the same, else the pulley would just remain stationary. So for this pulley to rotate, even though it's a tension on the left, a tension on the right, the one must be greater than the other for this pulley to rotate, else it's just going to remain stationary. The reason this happens is a bit more complicated to explain. It's because of friction between the rope and the pulley itself. So that friction now adds a distributed force over the length of the cable, and that in the end allows tensions to be different.